We will continue our discussion with balancing chemical equations. This is very important in chemistry because all the calculations that we do will depend on whether we have written correct and balanced chemical equations. We mentioned in the previous video that we cannot create or destroy atoms, and therefore the same types of atoms appear on both sides of the arrow, the reactant side and the product side. And we must balance the equations so that the same number appears on both sides for each of the atoms. For example, for this here, this is my reaction where I have hydrogen and oxygen giving me water. Remember, we also talked about how hydrogen will appear as H2 always, and oxygen will appear as O2 always in chemical reactions. So I've written H2 and O2 giving me H2O, which is the formula for each molecule. And then I have to make sure that each atom has the same number on both sides. This is a balanced reaction, so I can show you how to count, but I will give you an example in the subsequent slides on how to actually start. And I cannot stress this enough, and I will, for those of you who will have me in class, when we do these, this is the thing that I will stress the most. When we write molecules, so formulas for the molecules in a chemical reaction, we do not mess with the subscripts any longer. If the formula is correct, such as when we learned how to balance the charges for ionic compounds, the total positive charge had to be equal to the total negative charge, etc., or reading the name of the covalent compound and using from the prefixes to figure out what the subscripts would be by each atom, each element. In balancing chemical reactions, so this is my sentence now, right? I'm not messing with words anymore, individual molecules. In chemical reactions, we do not mess with the subscripts. They do not change. They are already correct because those are the formulas for the compounds. The only way that we can balance chemical reactions is by putting these numbers in front of the molecules called coefficients. When we balance chemical equations, we mess with coefficients which come in front of the molecules, not with the subscripts. Do not be tempted to change these bottom numbers here. We will only work with numbers in front of the molecules when we balance chemical reactions. These are referred to as coefficients. They're actually molar coefficients that tell us how many moles of each compound react together to form my products. And these are written to the left of the chemical formulas or right in front. How do I figure out how many atoms I have? Well, let's take hydrogen. On the left-hand side of the arrow, this is where hydrogen appears. I don't have another compound that has hydrogen. You could, depending on what the reaction is, and if you have two or more molecules that have the same element, you would add up all of those atoms in all of the molecules to get the total number of that element. But here, I only have hydrogen here. I don't have it here combined with oxygen somehow. To figure out how many hydrogen atoms I have, we multiply the coefficient by the subscript. 2 times 2 gives me 4 hydrogens. We do not add them, we multiply them. So 2 times 2 gives me 4. Now, it just so happens that even if you did 2 plus 2 would give you 4, but if you had a 4 here, that would be 4 times 2, 8, not 4 plus 2, 6. So 2 times 2 gives me 4 on this side. Well, let's go on this side now. Remember that in the molecule of water, so if I'm just looking at the formula for water, that subscript only belongs to the hydrogen, not to the oxygen. Therefore, when I figure out how many hydrogen atoms I have, I do the same thing. I have this coefficient that's in front of my molecule, so I will multiply the subscript by the coefficient. 2 times 2 gives me 4. Therefore, I have 4 atoms of hydrogen on this side and 4 atoms on this side. I could also work with moles. I have 4 moles of hydrogen here and 4 moles of hydrogen here all together. Either way that we look at it, I have equal numbers. Let's look at oxygen. Oxygen here doesn't have anything in front written out. It doesn't have a number. It's implied that there's a 1 here. We don't write 1, but it's implied that that's what it is. When I figure out how many atoms of oxygen I have, I will multiply my coefficient, which is 1, by the subscript, which is 2. So 2 times 1 gives me 2 oxygens. What about over here? Well, oxygen, this is liquid, so it's not, don't confuse it. This is G stands for gas, G stands for gas, L stands for liquid. Oxygen does not have a subscript here in the formula. That means that it's a 1. We don't write the 1, it's implied. That means that I have a 1 here. To figure out how many oxygens I have, I multiply the subscript by the coefficient. I have 1 oxygen times 2. That gives me 2 oxygens on this side as well. I have the same number on both sides. And that's how I know that a reaction is balanced. Let's take a look at an unbalanced. First, let's kind of mention a few rules on how to go about it, and then we'll practice one example. When we start, it would be easier for you to change the coefficients of compounds first before you change elements. So if I have CO2 and oxygen in the same, on the left-hand side as reactants, for example, start with CO2 first. Start with molecules and leave the elements to balance at the end. Because if you change the coefficient of the element, it only affects the oxygen here. But if I keep changing the coefficient of CO2, I change carbon and oxygen. And therefore, figure this one out first and then go, so compounds first and then go to elements last. Next, if you have polyatomic ions on both sides of the equation, let's say I have CO3 2-, so the carbonate anion. On both sides, treat these as units instead of splitting them apart and counting carbon, 1 carbon and 3 oxygens. You can say I have 1 CO3 unit or 2 CO3 units. If that makes it easier for you, I think it does, but everybody is different. If it doesn't, then split them and use the constituent atoms individually. There is no right or wrong way to do this, as long as in the end, each element has the same number of atoms on both sides. It doesn't matter how you get there. There can be multiple ways to get to the right answer. And I don't care that you do it my way exactly, so long as you know how to balance the chemical equations. And obviously at the end, when you think you're done, count twice to make sure that atoms or polyatomic ions are the same on each side as you change coefficients. Remember, if you happen to change a coefficient after you have, especially of a molecule, after you have balanced one of those atoms, make sure that you go back and count in case you have changed the other element, the number of the atoms of the other element, and then you don't account for them. That's why it's good to leave those elements for last. Let's take a look at an example. So I have C4H10, which is a gas, plus oxygen, which is a gas, giving me CO2 gas plus H2O gas. This is a combustion reaction, a complete combustion because I have only CO2 and H2O as products. Now let's take a look and see how many of each atom we have. Well, my coefficient here is 1. It's not written, but it's 1. So 4 times 1 gives me 4 carbons. What about on this side? I have carbon only on this molecule, and I have 1 times 1. I have only 1 carbon. Well, I have 10 times 1, 10 hydrogens, and on this side I have 2 times 1, only 2 hydrogens. What about oxygens? I have 2 times 1, I have 2 oxygens on the left-hand side. I have 2 times 1, 2 oxygens on this molecule, but I also have 1 times 1, 1 oxygen from the water, giving me a total of 3 on this side. So nothing is balanced right now. Here's the tally, right? Carbon, and you can write these out this way. Write out the types of atoms that you have, and then write how many you have on the left-hand side, how many on the right-hand side. Do the same for the others, and then see, okay, none of these are actually balanced. So my next step is to start somewhere. Let's start by balancing the carbon. Since I have 4 on the left-hand side, I need 4 on the right-hand side. I cannot put the 4 right here because that will change the formula of the compound, and I cannot do that. How do I balance my carbon? I put a 4 in front of the whole molecule. So see, I put a 4 in front of CO2. And now I have 1. My subscript is 1 times 4. That gives me 4 carbons on this side as well. Now let's tally to see how many do we have of each element now that I changed the CO2 coefficient. Well, my carbon is balanced, right? We said 4 times 1, that's 4 carbons. 1 times 4, that's 4 carbons. Good, so I've got one atom, one element, balanced. Now let's count hydrogens. 10 times 1 gives me 10 hydrogens. I haven't changed anything here to affect the hydrogen, so I still have 2 times 1, 2 hydrogens. Then I look to oxygen. I messed with a coefficient that affected the oxygen. So I have 2 times 1, 2 oxygens over here. I have 4 times 2, that's 8 oxygens from CO2, but I also have the 1 oxygen from the water to give me 9. So I have 9 on the right-hand side and 2 on the left-hand side. Now that I balanced carbon, let me see if I can balance hydrogen. And how do I do that? Well, I need to make this from 2 to 10. The only way I can do that, I cannot change this, obviously, but it is to put something, to multiply this subscript by something that will make it 10. And since it's 2, if I put a 5 here, 5 times 2 will give me 10. So let's take a look. Here's what I did. I put a 5 in front of the whole molecule of water. Note that I did not change that subscript. I did not change that 2 because then this would not be water any longer. But I can put a coefficient in front of that molecule, and that will give me 2 times 5, 10 hydrogens. Note that I didn't change the carbon, so that is still balanced. And now that I put a 5 in front of this hydrogen here, that gives me 10 hydrogens on the right-hand side, and I already had 10 on the left-hand side, which means that now my hydrogen is also balanced. Let's take a tally to see how many oxygens do I have. I still have 2 here. I have not changed anything on the left-hand side. But what do I have on the right-hand side? I have 4 times 2, that's 8, plus 5 times 1 is 5, so 8 plus 5 gives me 13 oxygens. Now let's figure out how to balance the last of these atoms, which is oxygen, and I need to make this 2 a 13. I could put 13 over 2 times 2 to give me 13 on this side. And then here's my tally. 4 carbons, 4 carbons. 10 hydrogens, 10 hydrogens. We had 13 oxygens. And then 13 and a half times 2, the 2 cancels with the 2, leaving you with just 13. So now the oxygen would also be balanced as well. The only thing that we need to change, however, is that in balancing chemical reactions, we do not like to write fractions. How do I get rid of this fraction? Well, I get rid of this fraction if I multiply by 2. If I multiply this coefficient by 2, though, I have to multiply all the coefficients by 2. And therefore, I would have to do 2 times 1, so 2C4H10, 2 times 13 and 13 halves, which gives me 13 oxygens, yielding 2 times 4 CO2 plus 2 times 5 H2O. So here it is. 2C4H10 plus 13 O2, giving me 8 CO2 plus 10 H2O. And the final tally, once again, when I think that I've already finished, I will do one more count to make sure that I am correct. 4 multiply subscripts by coefficients. 4 times 2 gives me 8 carbons on the left-hand side. 1 times 8 gives me 8 as well. So my carbon is still balanced. All I did is just multiply everything by 2. Now let's look at hydrogen. 10 times 2, that gives me 20 hydrogens. 2 times 10 gives me 20. My hydrogen is balanced. What about my oxygen? 2 times 13 is 26. Then remember that I have 2 molecules here that have oxygens, so I have to add all of those together. 2 times 8 is 16, plus 1 times 10 is 10, so 16 plus 10 gives me 26. And now my oxygen is balanced as well. But this was the problem in the previous slide because I used 13 halves. We don't like to write 13 anything with a fraction. And therefore, because the denominator of my fraction was 2, to get rid of the fraction, I needed to multiply everything by 2. Whatever the fraction is, if it were 3, I would multiply everything by 3. But then I have to multiply all the coefficients by that denominator to get rid of that denominator. Here is a sample problem. So balance the chemical equation for the aqueous reaction of barium hydroxide and perchloric acid to produce aqueous barium perchlorate and water. For this problem, I actually gave you the compounds, the formulas. For other problems, you would have to translate. So barium hydroxide, aqueous solution, we write with AQ. So barium hydroxide. What is the formula for barium hydroxide? Is Ba for barium, parentheses, OH2. OH hydroxide is the polyatomic ion with a -1 charge. Barium is a 2+ ion. To make this neutral, I need 2 OHs to 1 barium, and I would write that as a subscript. But once I write this compound formula, I don't mess with subscripts anymore. For chloric acid, it's HClO4, and I have it's an aqueous solution of that too. Then What happens is it produces barium perchlorate. This is my perchlorate and barium. So BaClO4 2 and water, H2O. Note that the both sides have atoms that are already equal on both sides. So barium, here I have one barium, here I have one barium. Now let's look at the hydrogens. I have 2 times 1, that's 2 hydrogens. And 2 times 1, I have, right, this is a 1. That 2 gets multiplied by the subscripts inside. So 2 times 1, that gives me 2 hydrogens over here, plus 2 hydrogens over here, 4 hydrogens. What about here? 2 times 2 gives me 4 hydrogens as well. So my hydrogens are balanced. What about the chlorine? I have 2 times 1, that's 2 chlorines on this side. 2 times 1, the subscript is not there, but that's a 1, it's supposed to be a 1, we just don't write it. 2 times 1, that gives me 2 chlorides. So those are equal to each other. And lastly, oxygen. 2 times 1 gives me 2 from barium hydroxide. What about here? I have 4 times 2, that's 8. So 8 oxygens from the perchloric acid and 2 from barium hydroxide gives me 10 altogether. What about on this side? 2 times 4 gives me 8, plus 1 times 2 gives me 2 from the water, 2 oxygens from the water, plus 8 from barium perchlorate gives me a total of 10, and now my oxygens are balanced on both sides. Practice a few of these on at least how to count the atoms first, and then practice a few on how to balance when you don't have a balanced reaction. That would be the first thing you do when you look at a chemical reaction, is to make sure that it is already balanced. If it isn't, the first step for anything that you're going to do from now on is to make sure that they are balanced. Okay, here's one for you to try. Butyric acid, also known as butanoic acid, here's the formula, is one of many compounds in milk fat. Write a balanced equation for the metabolism of butyric acid. Assume that the overall process of metabolism and combustion are the same. So we're writing a combustion reaction. Okay, what is a combustion reaction? Butyric acid plus oxygen. Remember how oxygen appears in chemical reactions. So these will be, the butyric acid and oxygen will be your reactants. They produce, so arrow, they produce carbon dioxide plus water. Those two, so carbon dioxide and water, will be your products. Go ahead and write the chemical reaction and balance the chemical reaction so you get some practice.